We aim to understand the following statement. The Stengurlach experiment measures the effect of an inhomogeneous magnetic field on a particle whose spin is in a superposition of states along the axis parallel to the inhomogeneity. Let us unpack this statement and explore the meaning behind the technical terms that were mentioned. We will start with the term spin. In classical mechanics, spin is just what common sense tells us. It is the property of turning or rotating in some kind of way. The more general term is angular momentum. And the solar system illustrates well the two main kinds of angular momentum. So we have orbital angular momentum. The Earth is moving through space around the Sun, and actually the Sun is also moving through space around the common center of mass of the system. And then we have spin, angular momentum, which is self-rotation of the Earth onto itself, or of the Sun onto itself. We characterize the spin of the Earth by an arrow whose direction lies along the rotational axis of the Earth and whose length is proportional to the rotational speed with which the Earth is turning onto itself. We now delve into the quirky world of quantum mechanics. Dirac in 1928 wrote the famous Dirac equation, which we will not delve into right now. We will just indicate that this equation shows, among other things, that the electron also has spin. Now, it is a bit intriguing because the electron is a point particle that does not have any special extent. And what does it mean for something that is just a point to rotate onto itself? Nevertheless, the electron behaves in many phenomena as though it were spinning onto itself. And this is why we chose to call this attribute spin. Now, the weirdness of quantum mechanics and electron spin does not stop here. We only just began. Let us go back to the spin vector that the electron also has with a twist. What do we need to specify a vector in 3 dimensions? We need 3 coordinates. For example, we could specify the 3 Cartesian coordinates. We have an x-coordinate, a z-coordinate, and a y-coordinate. But in quantum mechanics, the different coordinates of the spin vector are what we call incompatible. We cannot know 2 at the same time, and much less 3. As it turns out, we can only know one of the coordinates and the total length of the vector. This results in what could be called an indeterminacy cone. For example, in this animation, we know that the spin vector has a total length of square root of 3/4, and we know that the y component is equal to 1/2. And that only allows us to ascertain that the vector lies somewhere on this cone. All vectors lying on this cone have the same y component and the same length. We now turn to another peculiarity of quantum spin, and the etymology of quantum is at play here. Namely, spin is quantized in quantum mechanics. That means that, for example, the y component of spin cannot just take any value. Instead, it takes values in a discrete set. Successive possible values of this y component, which we will call the magnetic quantum number later on, are separated by 1. With all that in mind, we now turn our attention to the concept of the change of basis. The question we are asking is, given that I have a spin whose y component is known, what will I get if I measure its x component? One way to see that at an intuitive level is to project the indeterminacy cone onto the xz plane. We see that 2 values of the x component of spin are compatible with our state. The mathematical formalism of quantum mechanics actually shows that this y state is actually composed of 50% spin to the right and 50% spin to the left. This means that if you take numerous copies of your particle, all prepare them in the same initial y state, and then proceed to measure the x component, 50% of the time you will get x equals plus 1/2, and 50% of the time you will get x equals minus 1/2. In fact, the Stern-Gerlach experiment is just such a measurement. But before we return to it, we must talk about the magnetic moment of a particle. So, magnetic moment is present whenever charge is rotating in some kind of way. The spin possessing electron we just talked about is a good example. And as the name indicates, a particle with a magnetic moment will interact with a magnetic field, which is what is of interest to us. Mathematically, the magnetic moment mu is related to the spin s by a factor charge over mass. As a consequence, in the case of the negatively charged electron, we will get a magnetic moment that points in the direction opposite to that of the spin. Now, for the sake of simplicity, we will choose to consider another particle, the positron, which is positively charged. It is actually the antiparticle of the electron. It has all of the same properties, same mass, same spin, but an opposite charge, a positive charge. The anti-electron, also known as positron, was also a prediction of the Dirac equation that was confirmed a few years later by experiment. Let us now see what effect an inhomogeneous magnetic field like the one shown, which is increasing to the right, has on a magnetic moment. The energy is given by minus the magnetic moment times the magnetic field. Therefore, if I have a magnetic moment pointing in the same direction as the field, its energy will be negative. And we now appeal to this general principle of nature according to which a system will strive to minimize its energy. So this magnetic moment will try to get more negative. It will go towards the region of more intense field. On the other hand, if I have a magnetic moment that points in the opposite direction to that of the field, then it will have a positive energy. The minus signs cancel out. And it will try to get less positive. We are always striving to minimize the energy. In order to achieve that, it will go towards the region of less intense field. Now, if I consider again the spin with a known y component, I can ascertain what will happen to it in this magnetic field by recalling that it decomposes as 50% spin right and 50% spin left. So what will happen? Simply, each spin component will get correlated with opposite translational motions. It will dissociate in some kind of way. And now, in the case of the Stern-Gerlach experiment, it is just that with some y velocity as well. We are shooting the particle through the magnetic field. And this is what happens. You can see that as the particle traverses the field, each spin component acquires a certain horizontal momentum. And once they have exited the magnetic field region, they keep on going in straight lines. Let us now consider another kind of bullet that we are going to fire into the magnetic field later. Up until now, we have used a bullet of spin 1/2 who had two possible values of its y component, 1/2 or minus 1/2. Now we are going to consider a bullet of spin 1. The possible values of its y component are now 1. By symmetry, we also have minus 1. And we see that 0 fits right in between, with a spacing of 1 with respect to either of the other two values. Correspondingly, we will get indeterminacy cones for a y component equal to 1, a y component equal to minus 1, and the case of a 0 y component will be represented by a disk, which is kind of a degenerate case of a cone. If we know that the y component of a vector is 0, we know that this vector lies in the xz plane. Now, similarly, if we have a state of known x component, we have possible values 1, 0, and minus 1 for the x component of spin. We are going to set up our bullet in a state where we know the y component of spin to be equal to 1. And we are interested in how this state decomposes in the x basis. The mathematical formalism of quantum mechanics reveals that all three possible values of the x component of spin intervene in this decomposition, with the notable fact that the Sx is equal to 0 component, represented by the disk, weighs a bit more than the other two in this decomposition. Let us now place our spin 1 bullet in front of the magnetic field. We will decompose it into the x basis to understand its interaction with the magnetic field and shoot it. Notably, the 0 component corresponding to the disk is not deflected. And now let us consider things a bit further by talking about the measurement process. When our bullet interacts with something like this detector, a measurement occurs. In this case, a measurement of the position of the particle. Right before this measurement, the particle does not even have a well-defined position. It is a bit all over the place, we could say. All we know about it is represented by those two cones in this disk, namely the probability that we will find it at some place or another upon a measurement. The detector might register a hit in the middle, or it might register a hit on the left side, or it might register a hit on the right side. Now, if we prepare many bullets and fire them, we will see that there are more bullets landing in the middle, corresponding to the 0x component of spin, than on either the left side or the right side. This is because this middle component of spin weighs more in the decomposition of our initial state. We now turn our attention to another phenomenon which we call the magnetic shield. Let us go back to a spin 1/2 bullet, just as before. We decompose it into the X basis and shoot it through the magnetic field. The uncertainty in the spin is magnified by an uncertainty in the position, and let us focus on this left component that is entering a second magnetic field region. In this case, the magnetic field points along the Z direction, and we want to know what will happen, so let us change our vantage point, and we see that we have in fact just the same situation as before. It is not really a new phenomenon. What we have is an inhomogeneous magnetic field pointing in this Z direction. In order to ascertain what the bullet is going to do as it traverses this field, we decompose it in the appropriate basis. We decompose it as a superposition of known Z component of spin states. And just as before, each component will get deflected in the appropriate direction, and we see that we have missed our target, this big red ball. Let us now see what happens with a spin 1 bullet. We set up our spin 1 bullet in front of the magnetic field. We decompose it into the X basis. Let us shoot the bullet through the magnetic field. It dissociates. The disk is not deflected. It corresponds to the component 0. And we focus on this left component that is entering the magnetic shield region. We do the same thing as before. Let us change vantage points and decompose into the Z basis. Now, I hope you can see it. It is a bit faint because we are distributing the weight of the left X component into the 3 Z components that make it up. And I want you to focus on the disk here, which corresponds to a Z component of spin equal to 0. It will not be deflected by the magnetic shield, and we thus have a possibility of collision with the target. As an aside, I want to point out that the case of the X equals 0 component of spin represented by this disk over there is quite special. I refer you to the chapter of the physics of quantum warfare in my bachelor's thesis on getting familiar with quantum mechanics to see exactly why it happens to this component. Let us now turn to the final topic of this lecture, concerning the interpretation of the measurement process in quantum mechanics. The interpretation we have been using implicitly so far was first proposed by Bohr in the early 20th century, and it is to this day the most widely taught interpretation of the measurement process in quantum mechanics. As we talked about earlier, upon interacting with something like a detector, the bullet will go from having an undefined position with many potentialities to having a set position. This is wave function collapse, and it is an additional postulate that you have to add to quantum mechanics alongside, for example, the Schrödinger equation, which we have been implicitly using. It describes how simply quantum mechanical systems evolve with time, until, that is, you measure them. Schrödinger felt uneasy about this additional postulate of quantum mechanics, and it is in fact to point out the weirdness and the philosophical problems of this interpretation that he formulated his famous cat thought experiment. But let us now jump a few decades ahead and talk about Hugh Everett, a physicist who proposed an alternative interpretation of the measurement process. So, as we saw earlier, upon interaction of the bullet with something like a detector screen, we will get a collapse of the wave function, represented here by the two cones and the disk, to either the middle of the screen or the left part of the screen or the right part of the screen. Now, what the many worlds interpretation of Everett says is that all three outcomes occur, but each one in a distinct world or universe. During the measurement process, we, the observer, the measuring device, and in fact the whole universe become entangled with a particular outcome. And there is another us in another universe that is witnessing another outcome. So there is no random collapsing of the wave function anymore. The randomness now comes from the fact that we do not know which world we are going to end up in. Now, what comes next is not science. It is not even speculative science. It is pure fantasy. But I present it to you because it is a very interesting gameplay element. Imagine if we could in some way merge all three universes into a single universe in which all three outcomes occur. That way we could inflict 3 times the damage to the screen or to an enemy in a game. Now, this was not contemplated by Everett. It is not even compatible with the many worlds interpretation. For one thing, this so-called merger violates the conservation of energy, because we went from having one bullet capable of producing one impact to having 3 impacts. And violating the conservation of energy in such a spectacular way disqualifies this so-called merger as a hypothetical phenomenon of nature.